Non-deterministic Turing machines. You may have wondered where the N comes in the name of the complexity class NP. After all, the definition of the class says that certain things have to be done in polynomial time, not in non-polynomial time. The answer to that question comes from the following version of Turing machines called non-deterministic Turing machines. For non-deterministic Turing machines, the first three parameters, that is, the tape, the head, and the set of states, are defined exactly as they were for the classic deterministic Turing machines. The difference lies in f, which we call the transition function or program in the case of deterministic Turing machines. This f, which maps from s times A to S union yes union no, then times A, then times the set left or right or stay, was a function that is given a certain input consisting of a state and a symbol at the cell currently read. It sent the machine into a uniquely determined state. This is why those two machines are called deterministic. In an undeterministic Turing machine, the function f is replaced by the relation g, which maps from S times A, which is a subset of S times A, braces, then times S union yes union no, then times A, then times the set of collection going left, going right, or stay, such a braces. In other words, a non-deterministic machine has several legal courses of action in a generic step. Given a symbol in a cell and a state of the machine when reading that symbol, there are several ways in which the machine can continue. Fine, you will say, but when will we say that such a non-deterministic Turing machine T accepts the input stream X? What if a certain sequence of legal choices will result in T holding in the yes state and some other sequence of legal choices will result in T holding in the no state? Will we take a majority vote? It turns out that we will have a very weak notion of acceptance. We will say that T accepts X if there is at least one sequence of legal choices of action for T that results in T holding in the yes state. If there's no such sequence, we will say that T rejects S, X. With the acceptance of an input stream now defined, we can define acceptance of a language L by a non-deterministic machine T. This definition is not surprising. We simply say that T accepts L if T accepts L if and only if X is in L. How do we measure the running time of a non-deterministic Turing machine? We will not add up the running times it takes to carry out each computation that arises from a legal sequence of choices. Instead, we will define the running time of the non-deterministic Turing machine as the maximum running time among the running times of the possible computations. See Figure 18.2 for an illustration. We could interpret this definition by saying that in a non-deterministic Turing machine, all possible choices are followed up concurrently, so the total running time will indeed be the maximum individual running time. Figure 18.2 is measuring the running time of a non-deterministic Turing machine. Finally, we are in a position to explain the name of NP. The class NP is the class of languages that can be accepted by a non-deterministic Turing machine in big O of n to the k time for some positive integer k, where n denotes the size of the input. That is, NP stands for non-deterministically polynomial. Indeed, if a language L is in NP, then for x in L, a witness W of X can be verified in polynomial time by a deterministic Turing machine. A non-deterministic Turing machine could then just go through all possible witnesses for X and decide whether any of them are valid. As verifying a witness takes polynomial time, this non-deterministic machine would finish in polynomial time. If, on the other hand, no non-deterministic Turing machine could finish the task of checking all witnesses in polynomial time, then at least one possible witness could not be checked in polynomial time, implying that L is not in NP. Note that even this alternative definition of NP makes it clear that P which is subset or equals to NP, since a deterministic machine T is just a special case of a non-deterministic one. That is, it is a non-deterministic Turing machine whose defining relation G happens to be a function. In other words, in each step, T happens to have only one legal choice. The fact that we cannot decide whether P is equal to NP can be expressed by saying that in some sense, we cannot decide whether non-deterministic machines are really stronger than deterministic ones. Example 18.14. Let Ham CYC be the language of all undirected graphs G that have a Hamiltonian cycle. Then Ham CYC can be decided by a non-deterministic Turing machine T in polynomial time as follows. Let n be the number of vertices of G. Then there are n-1 factorial divided by 2 ways to arrange the vertices in a cycle. These will be the legal choices of T. No matter what choice T makes, T can then check whether that arrangement of vertices is a Hamiltonian cycle or not. In this stage, T can act as a non-deterministic machine and will still only need big O of n steps. So we find again the Ham-seq is in NP.